Okay, got 5 seconds before we begin. Good morning, Organic Chemistry 2341. Here we are on a nice Tuesday morning. We're going to continue on with Chapter 9 NMR. We're going to finish out Proton NMR or Hydrogen NMR today, also Carbon-13 NMR, and I'm going to introduce the topic of mass spec. Okay, so it's just so you know what it is, and there's some homework problems associated with it, but I just want to make sure you introduce that. So let me go ahead and share my screen. And let's see if that worked. Yes, it did. I'm going to put that over here. All right, I need to move this structure here. Can you all still see that screen? Proton Nmr Factors. Yes, all right. Okay, so remember, we're looking for 4 different things every time we look at an NMR. And those 4 different things give us something about the connectivity of the hydrogens associated with them. So we have the number of signals, so you're looking for number of unique signals. So when you go to the homework and you're trying to say, does this structure meet this? Does the structure look like this NMR? You can look at number of signals first. If there aren't the right number of signals for unique, it might not be that compound. Then you look for the relative intensities. Are there the right number of hydrogens available to you? You look at their positions, and then you also look at the spin splitting. That's going to tell you a lot about what's next to what, because we have those hydrogens within 3 bonds of that signal. So you can look for those. So like I said before, it's the number of unique signals we need to look for. And remember that we have through space interactions. The relative intensity of the area under the curve. So you can say there's 3 hydrogens here and 9 hydrogens there. Their position based on their chemical shift and their relative areas. More like hydrocarbons, the lowest, adding a little bit of electronegative element next to it increases it, adding an electronegative atom directly attached adds on it. The hydrogen, the amine hydrogen and oxygen hydrogen shift around a lot because of hydrogen bonding. Then we have alkenes, arenes, aldehydes, and carboxylic acids. Okay. And so now we're going to take on splitting. Splitting is the one that tells you exactly how many hydrogens are next to your peak of interest. Okay, so we said that the first rule is equivalent protons on the same carbon do not split each other's signal. So we get 1 signal for that type of hydrogen. Okay, and then we add the number of hydrogens that are within 3 bonds to that 1 peak. Our N is the number of hydrogens within 3 bonds. Our 1 is our equivalent protons we're looking at. And then we will see that they are forming either a singlet if there are no hydrogens within 3 bonds, or 1 hydrogen will give you a doublet, a triplet, etc. Okay, so we went through rule 1 and rule 3, but now I want to talk about some splitting patterns. Okay, so if you have 0 hydrogens within 3 bonds, that means you only have 1 peak because of the hydrogens you're looking at, and it will have a relative intensity of 1, and we call that a singlet, okay? Because we only have 1 signal, and nothing is breaking. Okay, I'm gonna shift networks real quick. I was unstable there. Okay, so now if we have 1 hydrogen within 3 bonds of the hydrogens of interest, we now have our N is 1, and so our multiplicity is 2. And so we have 2 equal height peaks. Those have the same intensity. We call that a doublet. If we have 2 non-equivalent hydrogens within 3 bonds, and it can go in either direction, we're just saying the total number of hydrogens, that'll give us 3. And that's going to be a 1, 2, 1 pattern. Okay, so these patterns keep going and going and going. Notice that the outer one is always leveled your relative intensity of 1. And then as you split them, if there's an even number, the 2 peaks in the middle are the same. If there's an odd number, the center peak is always the tallest. So what does that look like? Okay, well, that looks something like this right here. Okay, see how we have our relative intensities of the peaks are 1, 2, 1 for this triplet. And in theory, this is 1, 3, 6, 64, etc., as shown on the other chart. But let's talk about why we get that splitting a little bit first. Okay. So if we look at propane here, and we think about how many types of hydrogens we have, these two hydrogens are equivalent, and they're different than the other hydrogens, right? Because it's bonded to a carbon on either side, and each carbon on either side makes it different than any other hydrogens. Now, if we look at these B hydrogens right here, I think those are equivalent with these B hydrogens. And let's look at the connectivity right here. We have hydrogen to a carbon with three hydrogens on it. We have a carbon with two hydrogens on it, and we have a carbon with three hydrogens on it. Okay, if we go in that direction. If we go in the other direction, we see the exact same connectivity. What that means is all three of these are equivalent because they're on the same carbon, and these are magnetically equivalent because they have the exact same connectivity. So that means we have two peaks in our system. Now let's assign the splitting right here. So if we look at these hydrogens out here, so all six of these hydrogens give us one peak because they're all equivalent, right? So that's our one. And then let's find our N. It looks like we only have 1, 2, 3, 1, 2, 3. We have two hydrogens that are not equivalent to the B hydrogens within 3 bonds. So that means our N is equal to 2. So we have 2 plus 1 is going to give us 3 peaks. And that's what we see right here is our 3 peaks for all of these hydrogens, all 6 of those hydrogens. Okay. Now let's look at the B hydrogens. Okay, there we go. Now let's look at the B hydrogens. Oops. Let's do that. Okay. So the B hydrogens here, since they're all equivalent, I'm sorry, let's look at the A hydrogens now. We're going to look at these right here. Okay, so now both of those hydrogens are equivalent because they're on the same carbon and they're equivalent. So they get 1 peak. Okay, so 1 peak for that. But now we have 1, 2, 3, 4, 5, 6 hydrogens within 3 bonds of those hydrogens, which means our N is equal to 6. So 6 plus 1 is equal to 7. That means we should have 7 peaks in our next one. And if we look at it real close here, we do have 7 peaks. 1, 2, 3, 4, 5, 6, 7. And being an odd number, the center one is higher than the next two, which is higher than the next two, which is higher than the next two. And we see that pyramidal shape. And this is 1 to 6 to 15 to 20. You don't need to know the exact ratio. You just need to know that there is a fixed ratio for this. We'll see it each and every time. So what this tells us is that these two hydrogens, if we integrated, we know there are 2 hydrogens there, are next to 6 non-equivalent hydrogens. And these 6 hydrogens here, if we integrated it, are next to 2 non-equivalent hydrogens. So we can start building our structure by knowing that we have that many hydrogens near each of these peaks. All right, questions on that splitting? Okay. So sometimes it's hard to figure out. So there's some common patterns that we want to look at. And these common patterns are really easy to understand once you go through them a couple times, okay? So if we look at the green hydrogens here, and we see that if there's not a hydrogen listed here, it means it's bonded to a carbon or something else. Okay, so that means this green hydrogen is 1 peak by itself and is only next to one other peak, this red hydrogen here, which means it's going to give it a total of 2, which gives it a doublet. Okay, likewise, this hydrogen here is next to only one hydrogen, so that's 1 plus N gives us 2, and we get this pattern here. If we add a green hydrogen, okay, we still get 1 peak for the green hydrogen and 1 peak for the adjacent hydrogen, the non-equivalent hydrogen. So we still have a doublet here, okay? However, if we look at the hydrogen here, the red hydrogen here, it is next to 1, 2. It's next to 2 different hydrogens. So that means our N is equal to 2. So we have 1 for the red hydrogen and then 2 for the green hydrogen. So we get a triplet. Okay. Now, what if we changed it again, added another red hydrogen? Our green here is going to give us 1 peak plus 2 red hydrogens, triplet. Our red peak here is going to be of 1 peak for those red hydrogens plus 1 for each of the green hydrogens, a triplet. And then when we go to having 3 hydrogens here and only 1 red hydrogen, these 3 hydrogens are split once by the red hydrogen and we get a doublet. And this hydrogen is split by 1, 2, 3. So our N is 3. So we have a total of 4 peaks. And look at the shape here. We have the 2 in the middle are the highest and the next 2 are even as well. So just being able to recognize these patterns, you'll be able to quickly identify how many hydrogens are on adjacent carbons. And then of course, if we move up to a total of 2 red hydrogens and 3 green hydrogens, we're going to end up with 1 peak for this and 1, 2, 3, so a quartet. And then 1 peak for, 1 peak for all of these hydrogen plus 1, 2, giving us a triplet. All right, do we see how the N plus 1 rule works? Okay. All right, so if we have 2 methyl groups nearby, we're going to see that these have a total of 1, 2, 3, 4, 5, 6. So that means it split this hydrogen with 6 other hydrogens for a total of 7 peaks. We have 7 peaks here. And if we have no adjacent hydrogens, it doesn't matter how many of these green hydrogens we have, we're only going to have a single peak. All right, so that's how we do things for hydrocarbons, for straight chain hydrocarbons or any kind of functionalized thing that is considered a hydrocarbon or an alkene. However, once you get to aromatic rings, things get a little weird. And so we have a separate little section for aromatic rings. Okay, so what we'll learn a lot more about aromatic rings in the second half of this. We introduced the topic that benzenes were a alternating resonance structure here. And it's in a ring that lets us see each of these hydrogens slightly differently, okay? So in this particular one, we have these 3 hydrogens here, and this hydrogen and this hydrogen, that's 4 bonds away. So that means these peaks do not split. And that turns out it's this peak down here, okay? It's a hydrogen next to an aryl group, which is a little bit electron withdrawing, so it's going to be above hydrocarbon, but below everything else. Now, the remaining 5 hydrogens here are above 7. So all of our aromatic hydrogens are in the 6 to 8 range, okay? But because they're not equivalent, we actually start to see splitting, okay? And what do I mean by not equivalent? Well, let's look at the structure here, okay? Just by through space interaction, these 2 hydrogens that are next to this methyl group are different than these 2 hydrogens, okay? Do we see why? Because those 2A hydrogens are next to a methyl group, and these 2B hydrogens are not next to a methyl group, so they're different. So they show up in a different place. And because this C hydrogen is the only one that's by itself, doesn't have another pair, it also shows up in a different place. And so when we look at our peak here, we actually have them overlaying each other here so that we have really 3 different types of hydrogens, and the ratio is 2 to 1. But if we integrate the whole thing, we get a 5. It's a little bit easier to see when we have a bigger electron withdrawing group here, because we start seeing it split out a little bit more, okay? So in this case here, we added bromine. And just like before, we have our 2 hydrogens that are next to our substituent right here. And they are most influenced by this bromine, and so they're going to be shifted downfield. So they're going to be the highest ppm on the system, okay? Now, the next set is a little bit less, it's further away from the bromine. So it's going to be closer to having no substituent, which is closer to 7. And so that's one of the peaks under here. And then, of course, the C is going to be different than those, but it turns out because of electronics, it's going to be about the same place. So if we integrated this, we would see that we have 2 and 3. So it would say that we would have the 2 hydrogens for the benzene here, and then the remaining 3 hydrogens in the other side. And of course, bromine does not show up in proton NMR because it's not hydrogen. Questions about benzene rings. Okay. It's kind of like the other cyclos where you have to think about as unique because of their spatialness or because of their connectivity. Okay. So there's a really classical pattern when you have a para-substituted benzene ring. So when you have a para-substituted benzene ring, you end up with these 2 hydrogens being equivalent, these 2 hydrogens being equivalent, and so you get a pair of doublets. The one that's going to be higher field is the one closest to the electronic drawing group. The one less downfield is going to be the other one. And so we have this pair of doublets. It's a very distinct pattern for para-substituted or 1,4 substituted. Here's our 1, 2, 3, 4 as we go around the ring, just like in cyclohexane. So anytime we see that 1,4 substitution, we're going to see that kind of splitting. Another very common splitting is when we have something attached to an ethyl group. We have 2 hydrogens here and 3 hydrogens here, okay? And so what we'll see in this ethyl group here is another classical pattern where we have these are next to 3, so it's going to be split into a quartet, and we'll see a quartet. And these will be split by 2, so that's going to be a triplet. We see a triplet. Okay, so this is a classical pattern that was really recognizable. This doublet of doublets for a benzene ring above 7 to 8 ppm, and this ethyl group right here, the triplet quartet. Okay, so now that was the classical pattern for having them substituted in the 1,4. I'll relabel this here. 1, 2, 3, 4. This is 1, 2, and this is 1, 2, 3. So this is the 1,4 isomer, this is the 1, 2 isomer, and this is the 1, 3 isomer. Okay. In the 1,4 isomer, we get this doublet of doublets. Okay. But let's look at this 1, 2 here. These 2 groups are different, which means this hydrogen's different than that hydrogen. And these hydrogens are about the same. And so we end up with a total of 3 peaks. Right here. If we look at this 1,3 substitution, this hydrogen is different than any of these. And so we end up with a total of 4 peaks. So you might be able to just identify a homework problem just by looking at that pattern. All right, questions on proton NMR? Don't forget to look for spin, the number of peaks, the number of unique hydrogens, their relative intensity, their position, how far downfield or upfield they are, and the splitting pattern. Okay, now, the next most useful NMR experiment is when we use carbon-13, okay? So notice carbon-13 is an odd number, okay? The most common isotope of carbon is carbon-12. That's what 98% of all carbon is carbon-12. However, 1.1% is carbon-13, okay? So that means that, well, it's a lot less common than the hydrogen here, we can actually still see it, okay? However, because carbon-13 is so rare, we don't actually get splitting because the carbon, one carbon-13 next to another carbon-13 would be so rare because it's only 1%, we don't see any splitting. So there's nothing to split. So it simplifies our experiment. And the intensity is also kind of sort of relative to the number of things. We really don't usually use intensity in this. So that means we have 2 factors we care about with carbon-13 NMR. the number of signals observed, which means the different types of unique carbons, and their chemical shifts. And the chemical shifts are in the same order as those in proton NMR, although they're shifted a greater amount, okay? In proton NMR, we rarely see things above 10, except for aldehydes and carboxylic acids. In carbon-13, we're gonna see things all the way up to 220 or 230 ppm. So it's a wider range, but the relative position of the different types of things is the same. Okay, so let's talk about the number of unique carbons and where the chemical shifts might be. Oh, I guess we're talking about chemical shifts first. Okay, so just like before, the most like an alkane, the closer to zero. And again, in this system, zero is also the tetramethylsilane. So we're starting from that as our 0 point. So things most like alkanes are going to be closest to zero. Okay, then when you attach a electronegative atom, that shifts it higher. Okay, they can go as high as 70 or 80 ppm, having that there. They shift around a little bit depending on the nature of and the number of the halogens you have. The next thing we have is the CH2 that's next to an electronegative atom, but also is next to a carbonyl. In this case, it's an ester functionality, and those are shifted up higher as well. The alkynyl carbon, not the hydrogen, the alkynyl carbon is shifted up to the 60 to 90 because of that triple bond. But the double bonds are even higher, between 110 and 140. And benzenes are between 126 and 160. There's a typo on the slide. 125 to 160. So those are even higher than alkenes. Okay. And the only things that higher than a benzene ring in carbon NMR is the carbonyl for aldehydes, ketones, and carboxylic acids. So the carbonyl carbon itself. Notice the carbonyl carbon itself only had one signal in proton NMR. That was for the aldehyde, because it was the only one with a hydrogen directly attached. In this, we're actually looking at the carbon that has the double bond to oxygen. And they're all very high, 160 to 210. Okay. And the ones that are lower are ones that are bonded to electronegative atoms like carbon. The ones that are higher, the ones bonded to hydrogen and carbon. We'll see that as well. Okay. So let's talk about unique hydrogens and unique carbons and try to see how many peaks we should have. Okay. So if we look at this one here, we have a CH3 and a CH3. We might say, oh, those are the same. But this CH3 is 2 bonds away from a chlorine. This is 1, 2, 3, 4 bonds away from the chlorine. So they are not equivalent. Okay. So that gives us this as a unique peak. Then the carbon with the electronegative atom on it is going to be the highest downfield, and it's going to be unique because it's the only one with the chlorine on it. Then this one's going to be different than this one because it has 2 hydrogens on it, even though it's the same distance from the chlorine. This one's going to be next, and this is the most methyl-like, methane-like, and so it's going to be the farthest upfield, the closest to zero. Okay, so from just that relative intensity, we can say that this is going to be our first peak we see, the second peak we see, the third, the fourth, and the fifth. And you'll see that just by looking at that intensity, you can, just by looking at the connectivity, you can predict the relative area, the relative position in the system. Remember, we're only looking at position and number of peaks in carbon NMR. Did somebody have a question? Okay, so in this case, we should have a total of 1, 2, 3, 4, 5 peaks. And so we have 1, 2, 3, 4, 5 peaks. And our relative shifts are from 0 ppm to our highest, which is the one with the chlorine on it, which is in, remember, it's from 5 to 80, is where halogens show up. The carbon's bonded to halogens. Okay, let's add a carbonyl and show you where that shows up, okay? So again, this methyl group here is different than that methyl group here because this one is next to a carbonyl and this one's next to a carbon. So those are two unique signals. We definitely don't want to forget that the carbonyl carbon shows up in carbon NMR. And then we have our last peak here, so we should have a total of 4 peaks. And using that same prediction, we're going to say that the most hydrocarbon-like is going to be the lowest. Then the next most hydrocarbon-like is going to be there. This one's higher because it's attached to the oxygen. So it's going to show up in that 50 to 80 range, and that's why it's higher. And then the carbonyl shows up the highest. And in this case, because it's an ester, it shows up around 170. So it has that oxygen bond to it, which pushes it closer to where benzene rings show up, but it's still the carbonyl of this system. Now, one of the cool things you can do with the carbon NMR is you can do an experiment that changes the timing, and it can tell you how many hydrogens are on each of the carbons. And this is called the depth experiment, okay? So in the depth experiment, what they do is they actually take a slice of the NMR at different times. And at different times, that gives you a different part of the wave function. And so you end up with showing that you have either an odd number or an even number of hydrogens on your system. So let's look at this compound here and where it would be, just show up here. Okay, so we have a double bond. So we're going to have something in the 90 to 140 range. We have something with an oxygen on it. So that's going to be something in the 60 range. Then we have some hydrocarbony things. Those are going to be lower. Okay, those are going to be lower in intensity. So, but we can tell the difference between this C carbon from this G carbon by looking at how many hydrogens it has. This E has 1 hydrogen on it. This D has 2. This has 2. This has 1. This has 3. And this has 3. And this has 0. And this has 3. So that's how many hydrogens are on each of those. In this experiment, things with an odd number of hydrogens go up. Things with an even number of hydrogens go down. So if we look at where we have here, we can see that in our system here, and if they have no hydrogens on them, they disappear. Okay, so because F right here has no hydrogens on it, it actually goes almost to 0. Okay. We have 2 carbons with 1 on them. We have 3 carbons with 3 on them. So in theory, we should have a total of 1, 2, 3 for the methyl groups, 4, 5 for the ones with just 1 hydrogen on it facing up. And then we have 1, 2 carbons that should face down because only 2 carbons have 2 hydrogens on it. And if we look at the depth experiment, that's the 135, we see that the one with 0 almost goes away. This is 1 hydrogen and a 1 hydrogen for the alkene and the carbon with the oxygen on it. These are the 2 CH2s that are pointing down, and we have the 3 CH3s all facing up. And notice the CH3s are most hydrocarbon light, so they're the furthest up field. All right, questions on that? That's just an interesting experiment that lets you see how many hydrogens are each on that. It's called a depth. It's carbon-13 depth. Oops. It's that one. No, that's wrong. It's that one. Okay. So what I really want you to know about carbon NMR is you're going to look for 2 things: number of peaks of unique carbons and the relative shift position. And you should be able to figure out where it is. And then the depth experiment helps you identify which one has an odd number of hydrogens and which one has an even number of hydrogens. Okay, so now I want to introduce a concept called mass spectrometry. We did IR spectroscopy where we're looking at actual individual bond types. We've done proton NMR, which is showing you connectivity and adjacent protons. And we did carbon NMR, which was showing us where the different carbons are attached or how many hydrogens they have on. In mass spectrometry, we're actually going to look for the actual molecular weight and or how the molecule decompose. Like let's say you have a really weak bond, you're probably going to break that bond first, and you'll see that in mass spectrometry. So what it really does is you excite, you ionize your molecule, and it decomposes, and then it actually measures the weight of each little fragment that comes off. Okay, so in mass spectrometry, we have 4 things to consider. Number 1, the molecular ion peak. So that's going to be the molecular weight of the full molecule that you were trying to analyze. Okay, so it's going to be the actual grams per mole of the compound itself. Then from there, we go to the base peak. The base peak is actually the tallest peak on the spectrum. It is rarely the molecular ion peak because that molecular ion will break apart. The base peak, or the tallest peak, is going to be the most stable fragment. Okay, and we'll talk about that. And then the height of the different peaks gives you their relative abundance. Is it a very common fragment or is it an uncommon fragment? And then fragmentation pattern gives you an idea. For example, if you keep, if you see a peak and then minus 14, minus 14, minus 14, minus 14, that means you're taking a CH2 off, CH2 off, CH2 off, which means it might be a very long hydrocarbon. Okay, so this is what a mass spec should look like, okay? So we're gonna have our molecular ion peak, which is going to be the highest peak we see. Notice we don't see hardly any. Now there is a tiny little peak here that you can barely see, and that's from an isotope effect. So there's an isotope there that shows up. And if this is a carbon or hydrogen, that shows up about 1%. Okay. Then the next thing we see is the base peak. That's the tallest relative intensity peak. Okay. And then we look for stable ions. Okay. Notice this one right here is the molecular ion peak -1. These are masses right here, mass to charge ratio. So this is basically the molecular weight, and this is the relative intensity. And it's -1. Okay. Well, this is the structure for ethanol, which means that fragment there is when you removed the hydrogen from ethanol. So it's a good way to show that you have an alcohol because you've lost 1 peak of hydrogen. And then this fragment here is actually clipping off the OH, and that's just the ethyl group. So that is our major peak, is just this ethyl group right here. And so we can see the different fragmentation patterns, and that's going to be our base peak. And then these are different parts of, we're going to see OH, which is actually OH just down here, and we'll see other things. So let's look at another one. Okay. So when you get a mass spec in your homework, what you want to do is you want to look for the molecular ion peak. It's usually the highest one, or if it's the biggest to highest one, there's always going to be a little bit of 1% peak maybe. So it's going to be that one. And if it says your charge mass ratio is 105, that means your molecular weight of that main compound, the starting compound, is 105. Then you have to consider the possible formulas for that compound that has 105 molecular weight. Okay. So if you had a, let's say just a straight chain hydrocarbon, you're going to see it kind of break apart in little pieces. If you had an ester, you're going to see it make the carboxylic acid fragment and the alcohol fragment. So you're looking for those fragments and you can build them together. Okay. So there's some really common ions we'll see when we have things like benzene rings. Okay. So for example, we see this is our molecular ion peak right here. So that's our molecular ion peak. And so if we look at the compound here, the first thing we can clip off of here is a methyl group. So we're going to do minus 12, 13, 14, 15, minus 15. 12 for the carbon and 1 for each of the hydrogens. So we should see a loss of a methyl group. And we do. That's actually our base peak. It's our tallest peak, this loss of a methyl group. Okay. The next thing we can lose is this carbon and oxygen here, which gives us our next two peaks, which are these benzene peaks. And then this is that fragment that we lost here, the carbon, oxygen, and methyl group. So we can actually see by seeing what is leaving, what is being chopped off, the different fragmentation. And that's what we mean by fragmentation pattern. We look at the difference in mass between the different peaks here, and that tell us what part is being removed. So most of the time on our homework and on our exam, you can just look at the parent ion peak and maybe one fragment and figure out which it could be based on can these compounds make this major fragment. Okay. So let's talk about fragmentation. All ions tend to fragment to some extent. That's why the parent ion peak is rarely the base peak. So the base peak is your tallest peak, and it's usually the most stable fragment. Okay. So usually we kind of have this so that it fragments in a particular way. You want to do like regularly chopped off sections. Okay. So, and we don't know, we know the carbonyl. So one of the major fragments we see is actually the removal of a carbonyl compound, but it rarely removes as CO by itself. It usually removes with a CO and a methyl group. Okay, so we call that an alpha cleavage. So that means this fragment right here that we saw in the last one is really common. Okay, and that mass, we saw that mass right here, right at about 43. Okay, so that was a common fragment we see in carbonyl compounds. The other common fragment we see in carbonyl compounds is this fragment here, which is slightly larger. And it's usually found because you can make this 5-membered ring, it'll break apart and give us the specific thing. And it's called a McLafferty rearrangement. And there's one question on that homework, so you'll have to use that. Okay. Then the last thing I want to talk about with mass spec is there's actually a type of mass spec called high resolution mass spec. So everything we saw before, I was saying you have a mass to charge peak or a molecular ion peak of 40 or 50 or 105. Okay, that only tells you the gross molecular weight. However, if you account for all the different isotopes, you can get a average mass for each and every element down to 4 decimal places. Okay, and which means that you can actually get an exact molecular structure, molecular formula from using a high resolution mass spec. If you see something that has 4 decimal places and says the mass is this plus 4 decimal places, that's high resolution mass spectrometry. And that number equates to a single molecular formula most of the time. Very rare cases can you get more than one, but there's these huge tables when you can go look at that. But that's just something you can see and you can use as you go into your research labs. Okay, so mass spectrometry, I just wanted to introduce it to you, see what the structures are and what each of the things means. All right, questions on proton or carbon NMR or high res mass spec? Yeah, and I also teach a spectroscopy class, a senior level chemistry class where we use it very extensively. Okay, so now I want to switch gears. Okay, in module 8.1, we talked about how we can add a halogen to an alkene in an anti-Markovnikov's method. Okay, and we said we had to use a radical formation because it wanted to form, the halogen would come in first and form the most stable radical, which is the most substituted radical. Okay, so I've introduced the topic of radicals. Now we have an entire chapter on radicals, and we're going to start that today. Okay, so I'm going to reintroduce the concept of radicals and homolytic cleavage and some of the thermodynamics related to it, and then talk about the 3 steps of all radical reactions. Okay, so A free radical or a radical is just an unpaired electron. And you can have more than one on a compound. However, most of the time we're talking about a single unpaired electron on a single atom, okay? You can have multiples on a bigger molecules, but it tends to be in single. So we can have a hydroxyl radical or a one on carbon or one on bromine, okay? So almost anything can form a radical if it has the right kind of bond breaking available to it. So we talked a little bit about how it's sort of kind of a trigonal planar, but it has one electron in its p orbital, which brings it kind of down a little bit. It's still sp2 hybridized. However, it's not quite flat like a carbocation. Okay. And if we put in another electron in there and called it a carbanion, had a negative charge on there, it would even twist it down a little bit more. But in free radicals, we have a single radical in a p orbital, an unhybridized p orbital. So it's analogous to a carbocation, but it has different reactivity. Okay. So how do we get this? Well, the only way to get to the radical is you must have homolytic cleavage of a bond, meaning both groups leave with 1/2 of that sigma bond. Sigma bond has 2 electrons in it, so it breaks it apart, giving you 1 electron on each system. Okay, so how do we know whether something's going to do this or not? Well, we have to think about the bond dissociation energy of the different materials. And not only that, we have to think about the bond dissociation of breaking the bond. And when you break a bond, that is negative because you are taking away the stored energy and turning it into a higher energy state. When you form a bond, your bond dissociation is positive because you're taking a higher energy state of those single electrons and turning them into a more stable sigma bond. Okay, so this is a little bit of thermodynamics, but stay with me. Okay, so basically we can calculate whether the reaction is going to go or not by looking at the total energy of the system. And the total energy of the system is going to be our change in enthalpy, okay, because we're looking at the heat of the reaction. If it's exothermic, it's going to go spontaneously. If it's endothermic, it's not. Okay, so what we're looking for is something that gives off heat. Okay, so we have to look at the sum of all the different bonds being formed and the sum of all the different bonds being broken. And so that looks like the sum of the bond dissociation energies of the reactants minus the bond dissociation of the products, okay? Because the reactants were breaking bonds and the products were making bonds, okay? So in this case, if we looked at this right here, we have hydrogen has a bond dissociation energy of 436. Chlorine has a bond dissociation of this. We have to break one equivalent of that and one equivalent of that to make 2 equivalents of HCl. So that means we have to take that, which is the breaking of that hydrogen bond, and that, which is the breaking of that chlorine-chlorine bond. Okay. That gives us a total of this many kilojoules required to break the bonds and make them into their higher energy state. Now, we can make the HCl with just 432 kilojoules per mole, but we're making 2 equivalents of it. See, because we had 2 hydrogens and 2 chlorines, so we're making 2 equivalents of HCl. So we have to take that number times 2, or we get, so we have this number. And again, our products are negative because we're releasing heat to get to form that bond. Okay. So if we subtract the products from the reactants, we have a net enthalpy of negative 185 kilojoules per mole for every 2 moles produced, actually. A negative enthalpy is a release of energy. So it's releasing heat as it goes, and therefore the reaction is exothermic. And because the reaction is exothermic, it is spontaneous and will progress. Okay, so we can do this with any reaction, like a complex reaction like the chlorination of hydrogen, okay? And because this is a thermodynamic process, it doesn't matter what all the different steps are. All that matters is the starting step, which is the breaking of the chlorine-chlorine bond, or the breaking of this hydrogen carbon bond, and the formation of the carbon-chlorine bond and the formation of the hydrogen. There can be 100 other reactions going on, but it doesn't matter, because these are the ones that go from starting materials, the breaking of the bond, to the products. And that'll give us the net energy that is released or absorbed in the reaction. Okay, if energy is released in the reaction, it's exothermic. If it's absorbed, it's endothermic. So we can take that and start looking at it let's look at it from a reaction coordinate diagram. The first step is to homolytically break our chlorine-chlorine bond such that each chlorine walks away with one of the electrons from that sigma bond, okay? Now we're going from a made bond to a higher energy state, our radical state. We put energy into it, okay? So it has absorbed energy to get to that higher energy state. Okay, now, once that chlorine radical finds a methyl radical and they react to form a carbon-chlorine bond, now they're forming a bond. So they started at their higher energy state and then they formed that bond and are now at a lower energy state. And it gives off energy. And in this case, it's giving off more energy than it took to break that bond. If it's giving off more energy to farm the products than it did to make it, it goes into it goes forward and makes the new chlorine carbon bond. Okay. So we can do that as a list of calculations here too. The breaking of the chlorine-chlorine bond is going to be positive because we had to add energy to break that bond. The breaking of that carbon-hydrogen bond is going to be positive because we had to break that bond. The making of the carbon-chlorine bond is going to be negative because it's releasing energy. And the making of the hydrogen-chlorine bond is going to be negative because it's releasing energy. So by adding those together, we have the bonds broken, all positive. The bonds formed, and we have them all negative, which means we had a net release of 99 kilojoules per mole. So it's an exothermic reaction, and the forward reaction is favored. Okay, so again, it's only the bond breaking and bond making we care about. It can do 100 other things in the middle, but it doesn't matter. Okay, questions on heats of reactions. Okay, we introduced this once in chapter 6, but we're reintroducing here for radicals because it's a little different. Okay. All right, so now let's talk about the relative stability of different radicals, okay? So it turns out the relative stability of radicals follows the same lines as your carbocations, okay? Meaning your methyl or your primary radicals are less stable than your secondary radicals, okay? And so what we see here is that while there is a difference in that energy, it's not as big as with carbocations. So there's a difference and the trend follows, but it's not as big. So in the carbocations, it's more of a 25 kilojoules per mole. Here it's only 11. Okay, all right. So what we'll see here is that primary radicals are always less stable than secondary radicals, and secondary radicals are less stable than tertiary radicals. And so because this stability is a thermodynamic property, it doesn't tell us anything about the rate of the reaction. It only tells us what's more likely to form. The secondary will form at a lower energy than the primary. Okay, so again, it doesn't talk about rate, it only talks about energy. Okay, and so we can go with this table and do a bunch of calculations. We can see that things are going from stronger bonds to weaker bonds as we move. And we can trick that a little bit by making sure that we have our radicals form that are more or less stable than other things. And you'll use that table to do a couple of the homework problems. Okay. But there are some general trends, just like there was in acidity and basicity, there are general trends in bond dissociation energy as well. In fact, there's some of the same trends, okay? So the first thing is decreasing electronegativity decreases bond strength, okay? Think about that. The fluorine carbon bond is very short and very strong. So it's going to have a higher bond dissociation energy than something that is less electronegative. It's a slightly longer bond and a slightly longer bond. So decreasing electronegativity decreases bond strength, okay? The fluorine carbon bond is one of our strongest bonds. And then just look at our net electronegativity is moving across the periodic table, fluorine, oxygen, nitrogen, carbon, and their strength decreases as we move in that direction. So on the periodic table, if we go from fluorine to oxygen to nitrogen, it decreases their bond dissociation energy. Okay. The other thing that decreases that is the electronegativity decreases as bond strength decreases. It works with hydrogen as well. So if we think about the electronegativity difference between oxygen and nitrogen and hydrogen, oxygen and hydrogen have a more polar bond, and therefore it has a higher bond strength. And nitrogen and hydrogen have a less polar bond, and it has a lower bond strength. And carbon and hydrogen are said to have a non-polar bond, which is the least strong of the set. So the larger the difference in electronegativity between them, the shorter and stronger the bond will be. Okay. So the more polar the bond, the stronger the bond. Okay. And notice that kind of ties in with A here. The stronger the bond, the shorter the bond, the higher the bond energy. Okay. The next thing that we have is decreasing electronegativity and size increases. So just like we had when we looked down fluorine, chlorine, bromine, and iodine, the bigger the size you have, the longer the bond you have. The longer the bond you have, the lower the bond strength. All right. So think about the acidity as we move down, the ease of having that hydrogen leave got better and better as you got to iodine. And that has everything to do with the increase in size. So the bigger the size, the longer the bond, the weaker the bond. It decreases the bond strength. Okay. And just like in acidity of hydrocarbons, the decreasing S character decreases bond strength, okay? Which means our SP is going to be our weakest bond, our sp2 is going to be intermediate, and our sp3 is going to be our strongest bond, okay? Decreasing S character decreases bond strength. Is that? Yeah, no, I'm sorry, I said it backwards. The sp3 is the weakest, the sp2 is the middle, and the sp is the strongest. Decreasing S character decreases bond strength. So these are actually flipped around, but these are in the correct order. Strongest, most S character, weakest, least S character. Okay. Now, just like in carbocations, hyperconjugation will stabilize that radical, meaning that if you increase the amount of hydroconjugation available, it decreases the bond strength, okay? Which means our tertiary hydrogens are going to be much easier to remove than our secondary hydrogens, and our secondary hydrogens are going to be more easily removed than our primary hydrogens, and our primary hydrogens are more easily removed than our methyl hydrogens, okay? So our methyl is stronger than our primary, which is stronger than our secondary, and is stronger than our tertiary. This doesn't matter about the electronegativity, size, or hybridization. It's all about the idea that just like in a carbocation, the adjacent hydrogen-carbon bond can through space interact to stabilize that radical. Okay, so with that trend, we should see a big difference between the methyl radical, the primary radical, the secondary radical, and the tertiary radical. And we actually do see that as a significant difference. The methyl radical is right here high, almost 500 kilojoules per mole. The tertiary radical is only about 410. So there's almost a difference of 90 kilojoules per mole going from our methyl radical to our tertiary radical. All right, so the next trend we have is resonance increases stability of a radical, okay? Just like in acids and bases, resonance will help with stabilizing the radical. Because you're able to spread that radical out over more atoms, making it less reactive, making it more stable. So what that means is our tertiary is even higher in energy than our allylic, because our allylic can spread that bond apart. And so we have two places for that radical to be part of the time. In benzylic, because it can go all the way around the ring, it means it has 4 places we can spread that. So if we look at the resonance structures of our allylic radical here, we can spread the charge from, we can have the radical on this atom half the time, on this atom half the time, and on this atom half the time. And that's why it's more stable than that tertiary radical. That tertiary radical only has 1 place for that radical to be. In the allylic system, we can move that radical back and forth over 2. Okay. In the case of our benzylic radical, we can move that all the way around the ring to 4 different positions, 1 here, 1 here, 1 here, and 1 here. And because of that, it has 4 places for that electron to be shared, making it even more stable. Okay. So do you see how these trends are almost exactly like the acid-base trends we saw? Okay. Now, different functional groups can actually help, and it doesn't matter whether they're electronic drawing or donating. What it matters is, can it be conjugated such that it has more than 1 place for that radical to be? So even though this is an electronic drawing group, we can actually draw a resonance structure where we have the radical on the nitrogen and the radical on the carbon here. And because it has 2 locations, it is more stable than if it didn't have that functional group there. We can do the same thing with a ketone right here. It's technically a electronic drawing group too, but we can resonance stabilize the radical on a carbon or the oxygen. 2 positions, more stable. Okay. Now let's go to an alcohol. That's an electron donating group, right? Because it has lone pairs. Well, that lone pair can help by donating an electron to give us a radical on the oxygen and a negative charge, a counterbalanced negative charge on the carbon, so that we can spread that radical out over. Same thing with nitrogen. We're going to again take an electron from that lone pair and be able to have the radical reside both on the nitrogen and on the carbon. And so it'll be in resonance with those 2 different things. Because we have additional resonance structures, that makes the bond dissociation energy decrease, making it easier to break those bonds with the hydrogen next to those functional groups. Okay? So, questions on the general trends of radical stability. Okay. All these arguments should look familiar based on our acid-base concept. The only one that's really a little bit different is the fact that we can do that radical on both adjacent and 1 over atoms with conjugation. All right, we have 20 more minutes to finish up. So sometimes if you have something that is big and bulky, such that it kind of guards the radical, we can have what we call stable radicals. You're looking at either steric hindrance. In the case of this, we actually have 2 things happening. We have steric hindrance from these 2 big butyl groups, but then also that radical can be stabilized around that ring, okay? So we have both steric hindrance helping us keep that radical safe. And we have that electron stabilization, having that resonance structure, keeping us safe. Now, if we move over to something like tempo, right here, we have, again, a steric demand here, and a steric demand here, plus we can stabilize that lone pair with that lone pair on nitrogen here to help stabilize that radical. In the case of this big thing here, we can also stabilize it with the nitrogen here or stabilize it around the ring, okay, so that we can have both resonance and those electronic effects. Now notice we have 3 electronic drawing groups here, okay? That's going to make it such that any electron we dump into that ring is less of a negative charge because we have the electronic drawing group. So that's the electronic drawing group stabilization available to us as well. And then this one's a little different because this one's all about, it has steric hindrance, but it also has resonance because we can move this double bond and have that radical come over to this side. So that radical can be on either one of those oxygens. And so it's stabilized across that entire ring. Plus it also has the steric hindrance that lets it be stable. Okay. So these stable radicals are used in reactions so that we can start exactly a certain number of reactions at one time because you put in exactly a certain amount of these stable radicals and then move to the different parts of the reaction mechanism. Okay. So let's talk about the different parts of the reaction mechanism. All radical reactions have 3 steps, okay? They have an initiation step, which is when you form the radical first. You have a propagation step where it continues to react. And then you have a termination step. In the termination step, you are basically taking radicals and combining them to form a sigma bond. Okay, so those are the 3 steps. So the first thing we need to do is we need to initiate a radical reaction. And the most common way to initiate radical reactions is to use a weak bond that is easy to break homolytically. And the most common way to do this is to use the oxygen-oxygen bond. Okay. Because number one, both of those oxygens are the same. They're both electronegative. They both want to take electrons away. So they're more likely to break into 2 oxygen radicals than to break into an anion and a cation. Okay. So we can influence the stability by adding different things to make these easier to break or harder to break. The easier to break ones actually start initiating at lower temperatures. So you'll notice an easier to break bond. So let's look at 2 examples. This is Diter butyl peroxide. So the idea here is this oxygen-oxygen bond is the peroxide. That oxygen-oxygen bond is the weakest bond in our entire compound. So if we heat this up to between 100 and 130 degrees, it's going to have enough energy to break into 2 oxygen radicals. Once we form that oxygen radical, it can then react with something with a stronger bond. Okay. We use an initiator because it has a weak bond that forms radicals. And then we can use that in the propagation steps to make the other stronger bonds react. Now, because there's a possibility of conjugation and electronic drawing here, this actually breaks more easily. And this is dibenzoyl peroxide. It's different than the stuff used in medications. It's actually a benzoic acid peroxide. So what we can do here is, again, this oxygen-oxygen bond is the weakest bond. And because it's so much weaker than our T-butyls here, it actually decomposes much closer to room temperature, between 60 and 80 degrees. And it'll generate this benzoxy radical, but then it's going to eliminate CO2 and give us our phenyl radical. And that's the actual reactive species. Okay. So again, we initiate usually with something like a peroxide because that's the oxygen-oxygen bond's very weak. And it gives us a 2 equivalents of radical for our next step. Okay, so I said there are 3 steps. So let's look at the next step. Okay, so, let's look at all the steps. And we're going to use chlorine of the chlorination of methane, okay? We have carbon-hydrogen bonds. They're not reactive to nucleophiles, and it's almost a nonpolar bond. So almost any other reaction is not going to work with breaking that carbon-hydrogen bond. So that's why radical reaction mechanisms are very, very valuable for our, chemistry of the hydrocarbons. Okay. So the first step we do is our initiation step. And in this case, because we're using light, which is the H nu there, we can actually break apart the chlorine-chlorine bond. Even though it has a fairly high bond dissociation energy of 430, we can actually hit it with light and it'll break apart. Again, it's breaking apart homolytically because we have two chlorines that are the same electronegativity. And so it's easier for them to break out homolytically, giving a radical, than have one leave with a positive charge and one leave with a negative charge. Okay, even though that's a pretty big bond dissociation energy, it's always going to break into two radicals. Okay, so again, with this initiation, we only need a little bit of this to actually form this two equivalents of chlorine radical. Okay. And the reason is because in the propagation step, we're going to continue to generate radicals. Okay, propagation, a radical is going to react with a neutral substrate to generate a radical. That radical is going to then react with a neutral substrate to form a radical. That's going to react with a neutral substrate to form a radical. So every time a radical reacts with a neutral substrate, it will always generate another radical. So that's why it's called the propagation step. So in this case, we're going to use that chlorine radical, and it's going to use one of its electrons and break this carbon-hydrogen bond to give us a new sigma bond and another radical. Okay. So let's look at that. We're breaking that nonpolar hydrogen-carbon bond by using only one electron, right? We're going to use one electron from that sigma bond, and so that other electron stays behind on the carbon. We've generated another radical, okay? So the next thing it can do is that radical now can react with a neutral molecule of chlorine to create a new chlorine-carbon bond and generate another radical, okay? So that's why we only need a little bit of that chlorine radical, because once we use it, it creates the carbon radical, which then can react with neutral chlorine. Okay, so does it stop there? Well, no, you've got 4 hydrogens on there. The hydrogen carbon bond is weaker than the hydrogen chlorine on the chlorine carbon bond. So it's going to continue to go. So what happens? It reacts with another equivalent of the chlorine radical, which you just generated. I'm going to change colors here. So you just generated this one. So it's going to react with another one. Notice this one already has a chlorine on it, but there's nothing stopping it because the hydrogens are going to have the same bond dissociation energy. So there's no reason for it to react with one with chlorine or one without chlorine. So when it does, it generates an equivalent of HCl and a new radical. That radical then reacts with neutral chlorine, which gives a chlorine radical. And it continues to go on and on and on until you use up all the chlorine or all of the hydrogens. Okay, so now you have to stop the reaction. And the stopping the reaction is called the termination step. In the termination step, we've probably used up all the chlorine possible, and we'll end up by combining a chlorine radical with a chlorine radical. There's a typo here. Chlorine radical. Okay. So 2 chlorine radicals will terminate to make a chlorine molecule, which then can react if there's other molecules there. Okay. The other thing and this is a termination step because we had 2 radicals making a neutral compound. Every single one of those propagation steps, we started with a radical and produced a radical, started with a radical and produced a different radical, started with a radical and produced a different radical. The termination step is where you combine 2 radicals to form a sigma bond, and therefore stops the generation of our radicals and therefore terminates the reaction. The other possible thing is you have a chlorine radical reacting with a carbon radical. That'll give a nice product here. And the least likely is, but does still happen, you can have a carbon radical react with a carbon radical. And it's a little bit about sterics, which is why it's the least likely to happen. But any type of reaction where a radical reacts with a radical to generate a neutral molecule is a termination step in our system. Okay, so let's talk about our 3 steps again. Initiation, the generation of your first radical. And we can do it with a peroxide, or in this case, we did it with light. Propagation step, you take a radical and make a different radical, and you keep doing that. Termination, 2 radicals together to form a neutral compound. All right, questions on the 3 steps of radical reactions? Okay, got 10 minutes left. Let's power through here. Okay, so if there is no nucleophilicity, or we're not talking about nucleophiles here, is there a difference in reactivity between the different halogens? And well, there should be, because they form different bond, they have different bond dissociation energy, and they form different bonds from different things. You know, they'll form different strengths of bonds as they move. Okay. So if we look at the reactivity of these things, it's going to be more about the rate of reaction is going to give you selectivity of reaction. The faster the reaction goes, the less selective it's going to be. The slower the reaction goes, the more selective it's going to be. Okay, so let's see if that's true. Let's look at this right here. Okay, so if we wanted to do a general reaction where we have propane, okay, 3 carbons propane, and we are going to halogenate it, right? Statistically, we should see there's 2 hydrogens to replace here. There's a total of 6 hydrogens to replace there, giving us approximately 2 and 8. So 25% of the product should be reacting here because there's 2 hydrogens, and 75% should be reacting there because that's a total of 6 equivalent hydrogens. Okay, so if everything was equal, we would see 25% and 75%. Okay, when we do the reaction with chlorine, we don't see that. We see 57% at the least likely side and 43% at the more likely side. So what is that telling us? That's telling us something about it's waiting for the secondary radical. Okay, so it has a little bit of selectivity. It's going to wait for that secondary radical because it wants to form that bond on that secondary site. Let's look at bromine, 92%, 8%. So bromine is even slower in the fact that it's going to wait for that secondary radical to form before it reacts. It's going to be more selective. Okay, and iodine actually doesn't do this. It's not reactive enough. But let's look at fluorine. Fluorine reacts in the statistical, or pretty close, 29 to 70. Okay, so it is most like the statistical side, meaning it's least selective. It's going to react with whatever radical is there first. So it's going to match the statistical side of it. All right, so, but there's going to be a reason for this, right? So it's all about the rate of the reaction as to whether it's selective or not. Okay, so let's look at the relative energies to start doing this right here. Okay, so if we're looking at the bond breaking and bond making steps here, we have to break bonds, we have to break a primary methyl group, a primary hydrogen, and that takes 422 kcals per mole. Okay, and when we look at the breaking of each of these, okay, notice that fluorine has a bond dissociation of 159. Chlorine's higher, then bromine starts coming down, and iodine's a little bit below that. So we're looking at the slightly different distribution there. And if we think about the bonds being formed, we're going to form one equivalent of the acid from the other half of the halogen and 1 carbon halogen bond. Okay. And if we looked at that, the formation of the fluorine bond is stronger than the chlorine bond, which is stronger than the bromine or the iodine. So this is going to release more heat as it goes. And if we look at the net result, the net delta, we have a negative 464 versus negative 118 versus negative 84 versus iodine, which is actually positive 39. That's why iodine doesn't work. It's an endothermic reaction. It does not favor going to products because it would take energy to make that bond. But notice fluorine gives off 4 times more heat than the reaction for chlorine. Okay, so that 4 times more heat is going to tell us that it is going to be much less selective. It's going to react as fast as possible. Okay, now that's with the primaries. Okay, so we have very fast with the fluorine right here, and then iodine doesn't go at all because of the positive net enthalpy. Let's look at the formation of the secondary. The secondary is easier to form, right? It takes less energy to form a secondary radical. And what we see is that secondary radical is a little bit easier to form, 12 kcals per mole, kilojoules per mole. But the bond dissociation energies of the halogens is the same. Now let's look at the bonds formed, okay? The formation of the acids is identical because we're forming just the same acids. However, the bonds formed for the secondaries are slightly, either slightly higher or about the same, okay? So if we look at the net reaction, we still have a very high enthalpy given off, and we have chlorine and bromine are lower. So notice that we have the difference between these is not very high, okay? And the difference between these is not very high. So that means that both reactions give off about the same amount of heat as they progress. And so there's no big barrier between them. Okay. Okay. But the other reactions give off less heat. The less heat that's given off means that they don't have to react as quickly. They can wait around for the more stable radical and therefore give a higher yield of the secondary halogen. Okay. So if we look back at our numbers here, fluorine is about statistical, about the same amount of energy, but much, very, very exothermic, very reactive, very fast. The chlorine and the bromine were less exothermic. Therefore, it slows the reaction down and it can wait around for the secondary radicals. Okay, so let's do just a comparison of the fluorine versus the iodine. We saw that the fluorine was very exothermic reaction, right? Because it had a negative 450 to 480 kilojoules per mole. Okay. Iodine, however, if we looked at the bond strength of the carbon iodine bond and the hydrogen iodine bond, they're actually weaker than the iodine-iodine bond, okay? But the iodine radical itself is stable, but there's no driving force for it to react with the carbon-hydrogen bond because that would take additional energy. It was endothermic, okay? So let's talk about location, okay? The abstraction of the hydrogen from the fluorine and the chlorine is extremely exothermic. In bromine, it's slightly endothermic. Okay, so that means the primary hydrogen is more exothermic in fluorination and chlorination reactions. Therefore, we're going to get a higher amount of it. The larger difference between those bond dissociation energies means that chlorination is less exothermic for both primary and secondary carbon radicals, or the abstraction of those primary and secondary hydrogen. And bromine is pretty stable radical and just will form very weak bonds with those. Okay, and therefore, in addition, the bromine radical is endothermic when trying to extract that. See, that's going to slow things down. Okay, so a primary hydrogen being pulled off by the bromine radical is endothermic. The primary, the pulling off of a secondary radical is slightly less endothermic, making it favored. If it's favored, it's going to be the larger amount of product in your system. All right, that brings us right to 9:20. So what I'm going to do is I'm going to go ahead and stop recording. If you want to ask questions, stay behind. If not, we'll continue this on Thursday.